Asteroids exchange material in slow motion, cosmic snowball impacts. NASA data reveals recent analysis of images from NASA's Double Asteroid Redirection Test. DART mission confirms that asteroids aren't static rocks in space. Instead, they slowly exchange debris like throwing cosmic snowballs, reshaping their surfaces over millions of years. This discovery provides critical new insights into asteroid evolution and how they may pose a threat to Earth. Evidence of material transfer. The DART mission, designed to test asteroid deflection technology, captured the first direct visual proof of this phenomenon. Images taken moments before the spacecraft deliberately crashed into the asteroid moon Dimorphos revealed faint, fan-shaped streaks across its surface. Researchers initially questioned the images, suspecting camera or processing errors. However, further analysis confirmed the streaks were formed by rock and dust debris drifting from Dimorphos, companion asteroid, Didymos, and settling onto its surface via extremely slow impacts. The discovery is important because it demonstrates asteroids are not isolated bodies, but dynamic systems constantly interacting with their environment. About 15% of near-Earth asteroids are binary systems, making this material exchange a common process: orbit alteration and AMP. Systemic shift beyond material transfer. The DART mission also demonstrably altered the binary asteroid system's orbit around the Sun. The shift was subtle, about 1.7 inches per hour, but significant. Over time, even minor orbital changes can determine whether a potentially hazardous asteroid will intersect with Earth or pass safely by. This systemic impact underscores the power of targeted kinetic deflection, a key element in planetary defense strategies. The role of asteroid spin and AMP. The YORP effect. The research builds on existing knowledge of asteroid behavior, particularly the YORP effect. This phenomenon explains how sunlight can gradually spin up small asteroids until loose material breaks free. NASA's Lucy spacecraft has observed similar equatorial ridges on other asteroids, formed by material accumulating after spin-induced shedding. Dimorphos and Didymos share these features, suggesting a widespread mechanism for surface evolution. The debris from Didymos landed on Dimorphos at approximately 12.1 inches per second, slow enough to deposit material rather than create craters. The streaks align with models predicting where ejected material would accumulate, confirming the process. Future missions and AMP. Planetary defense implications. The European Space Agency's Hera mission, set to arrive in December, will conduct a detailed post-impact survey of Dimorphos. Scientists hope to determine if the fan-shaped streaks survive the collision and identify new patterns created by debris ejected during the impact. This data will refine asteroid evolution models and improve planetary defense measures. We now know that asteroids are far more dynamic than previously believed, stated Jessica Sunshine, study lead author. This knowledge is crucial for accurate risk assessment and the development of effective strategies to protect Earth from potential asteroid impacts.